Have you ever thought about things that fade away but never seem to, truly disappear? It could be a memory or something a lot more serious, like nuclear waste. Well, it turns out there's this really cool and honestly kind of unsettling mathematical rule that runs the whole show. Okay, let's dive in.
So this is the big question for today. When you hear that something has a half-life of thousands of years, what does that actually mean? Does it just poof, vanish one day? Or is something else going on? Let's figure this out.
All right, first up, the forever problem. And this is not just some abstract idea for a math class. Nope, this is a very real challenge that people have to deal with in the real world.
So at its core, radioactive decay is totally natural. You've got this shaky, unstable atom, and it just wants to chill out and become stable. To do that, it lets go of some energy. Simple, right? But here's the weird part. It doesn't happen all at once. Instead, it just kind of fades in a way that seems to go on, well, forever.
Okay, Section 2, Growth versus Decay. To really get our heads around this forever problem, we've got to look at the math that's pulling the strings, exponential functions. And what's wild is that the very same code that describes something growing like crazy also describes this endless fading.
And it all comes down to one tiny difference. Check it out. For growth, the base, that's the number you keep multiplying, is bigger than 1. So if your base is 2, things double, and double, and double again. But for decay, the base is a fraction, something between 0 and 1, like 1/2. Just by making that one change, the whole story flips from doubling to halving.
And that right there is the key. That base number is everything. It's like a switch on a train track. If it's greater than 1, you're on the express train to huge numbers. But if it's less than 1, you're on that long, slow journey towards 0 that we're talking about today.
So next up, and this is where it gets really mind-bending, we're talking about the line it never crosses. I mean, if the amount of radiation keeps getting smaller and smaller, why doesn't it just hit 0 and, be done with it? Well, the answer is this fascinating invisible boundary in math. And this invisible boundary has a name. It's called an asymptote. Just think of it like this. You're running a race, and every second you cut the distance between you and the finish line in half. Then you cut that new distance in half, and again and again. You get unbelievably close, but mathematically, you never actually touch the finish line.
Okay, so let's connect the dots here. We have our radioactive material that keeps halving itself. And we have this weird math rule, the asymptote, that says the graph never actually hits 0. So what's the big takeaway? It means that, from a pure math perspective, the radiation never ever truly disappears. The amount gets cut in half, and then that little bit gets cut in half, and so on, down to these impossibly tiny amounts. But the quantity never actually hits a flat, absolute 0.
Let's just look at the raw numbers to see it plain as day. Say you start with 1 unit of this stuff. After 1 half-life, you've got half left. After 2, you've got a quarter. After 3, an eighth. You see the pattern, right? The number just keeps on shrinking, getting closer and closer to 0, but it never actually lands there.
And this quote just nails it. The math of the asymptote isn't just some theory. It's a perfect model for why radiation is so persistent. It's the mathematical reason why nuclear waste is a problem we have to think about on these just massive timescales.
All right, final section, a universal math law. And what's so amazing is that this rule isn't just for atoms. Once you see this pattern, you start spotting it in completely different parts of your life, from physics all the way to your bank account.
Yeah, this isn't some obscure formula that only works for one little problem. It's more like a fundamental law of the universe that describes change itself. It explains how things grow and how they fade, which makes it one of the most powerful ideas in math.
So get this, the exact same mathematical logic that describes the slow fade of an atom also describes explosive population growth. And it's the same logic behind compound interest that makes money grow in a savings account. They're just mirror images of each other, all governed by that same rule. It just depends on that one thing. Is the base bigger than 1 or smaller?
Now, if you want to sound like you know what you're talking about, mathematicians use a couple of key terms here. The domain is just the inputs. In our case, that's time, which is always moving forward. And the range is the possible outputs, the amount of stuff that's left. And because of our friend the asymptote, that amount, the range, is always greater than 0.
So if there's one thing you walk away with, it's this. Exponential decay is the mathematical blueprint for anything that diminishes over time but never fully vanishes. It's like the ghost in the machine, that echo that never quite fades to silence. So I'll leave you with a question to chew on. Now that you know the pattern,
This idea of something reducing by a fraction of whatever is left, where else do you see this hidden mathematical rule working in the world around you? Once you start looking, you'll be surprised where it pops up.